7.5 meters of length. Prepared by me. Then, the first of the project is the contents. The content is the requirement of the ownership. Then, the line forms. Next, the general distribution of the ship. The structural analysis, that is very important. The propulsions. The economic analysis, that is so important for the ownership. Then, the conclusion that I have for this project. First of all, I have the introduction. The introduction is, for this project, I use the spiral design that is like a cycle. Then, I had the requirements. What is the requirements of the ownership? The ownership say me the construction of the boat is type a jab. That this jab is for a steel material. The yacht has a capacity of 18 passengers. That they say me the ownership. The velocity is around the 11 knots, and the yacht will be used for transport of passengers that will make the tourists in Galapagos Islands. Here I show you a graph of the Galapagos Islands, and here is my route to the Isabela, Santa Cruz, Pinzon, and then next to Isabela. Then next to the dimensions. For the dimension, I use the regression, the linear regression. I use 3 models for to do my regression linear for to hide my dimensions. Here in Excel, I use the linear regression for to calculate the beam. And here I have the calculation to assume a length, and the beam is 6.6. Then for the draft and the depth, the similars too. We continue. I have the table, that the main dimension of my passenger ship. Then the line forms. The line forms, I use a program like a Maxwell program, and I model the ship for to use some calculation that is so important for the ship. And here I the models, and then the calculation. The calculation is here for the different draft. So important, the flow coefficients, prismatic coefficient, the KB, the KG, and all of displacements, and all of these calculation for the model for to have the construction for the passenger ship. Here I show you the graph for the different draft with the displacement and all of the calculation that I said you before. Here's another graph with a different draft. And next, the general distribution. The general distribution of the passenger ship that I have is 9 rooms. That means that 1 room is per 2 persons by room. And here the distribution, that's a bar, a chicken, that is so important in a passenger ship for the persons, and have a general distribution of a ship. Then the structural analysis. For the structural analysis, I use a standard ISO 12215. I read an article, and here at the boat design, I have to be is the range is here, the minimum, the maximum, and we see that I am in the range. That means that I can use the standard ISO. Then I did the calculate and the different pressure of the ship. For example, the pressure at the bottom is the 26 kilonewtons divided by meters square. The pressure of the side, the pressure of the deck, and the pressure of the deck, and I have all of the pressure around the ship. Why I calculate the pressures? Because it's so important for the article to have the thickness of the plates. Here's the all pressures, that's so important, and then the thickness, the minimum thickness that I put in the ship. For the bottom, for the side, for the deck, for the superstructures, and for the bulkheads, here I have in meters and millimeters. This is the thickness for the plates. Then, in the article, say me that I have the thickness and I calculate the minimal sectionals, the modulus sectionals, and then in a table, I have the reinforcement. For the reinforcement is in T. Then the propulsions. For the propulsion, I use hull speed. For hull speed, like a velocity 11 knots. And the program put me this graph. And I enter in the graph that I say you that the velocity is 11. I here, and we put to the HP, that is the power, is around 260 horsepower. And I select the motors in the internet, and I select the diamonds C6, C8, output 0.3. Then the most important thing for the ownership is the economical analysis. For the economical analysis, first of all, I have to did a list of all of the things that I have to buy. For example, for the whole superstructure, I have that's price, and then for the propulsion, the list of the propulsions, the list of the accommodations like bed, sofa, chicken, all of the things. For the navigation and salvage, that is so important because it's a passenger ship. For the circuits, that so important, and the hull protections. Then I have the list, and then I put in a table with the like a resume. And like a resume, I have the total for my cost of this passenger ship is $1,844,000. Then the expenses. I have some expenses of this. For example, the personal salaries. The personal salaries, I have nine tripulants, one guy, and the captain. And I multiply, and I have these results, the fuel, the permission, the limitation, the publicity is so important because in the Galapagos Island is a lot of competitions. The agencies that I put here in Guayaquil, and I have the total expense. This is the balance. And for earnings, I have the time, annual, height, and annual. This I divided by the rooms, 1 to 6, 9 to 10, 7 to 8. For the passengers that I have to 1 to 6 is 12 passengers, for 9 to 10, 4 passengers, and 7 to 8, 2 passengers. I have like a table. I assume that 3 nights per week is so good. I hear the earnings for months and earning for years. I have this value for the earnings. Then the inversions. The bank lent me the 80% of the cost, and the ownership put the 20% of the ship, the value. The bank say me that they put me the interest of 14%, and I calculate for the 14% for 5 years. And then I calculate that I want to win the 15%, and then for the 30%. Then
how much did you ask to the bank?
What?
How much did you ask to the bank?
How much? The 80% of the cost of the ships. 80%. Yes. Then I calculate the bank that is saying me that the project is good or not good. For example, for the 30% is like a minus, that is not so good, but for the 15 is very good. That means that I calculate the tire IR, and this as 29.3%. Then this the benefits divided by the cost of the ship, and this is 1.4. And say me that is more than 1, is so good the project. For conclusions, for my conclusions? The yacht was very efficient in accordance with the requirement of the ship owner, because I did all of the requirements that the ownership said me. Then the design of using the knowledge learning in our last course, because I used for today's the project, I used the last course that I passed before. Then the project is economically very good, because I explained yours that it's very good because it's more than 1. Definitely, I will earn money with this project because I will buy with this project. Thank you.
Start the presentation. First, I want to ask this question: What do you think when you hear the steam plant term? Some people think in this: an old ship, a 19th century ship with the steam start, the propulsion in the ship. But now, most of the special ship have a steam turbine in the propulsion with LNG, like LNG ship, the Navy ship, even aircraft, submarines, the propulsion is generated by a reactor, a nuclear reactor, but heat the water, and this is the propulsion in this ship by the steam turbine. Like this, I like the title of the presentation: a selection of the principal equipment for a 4,000 kilowatts steam plant. In the schedule, we have objectives, Rankine Cycle, Thermodynamical Analysis, selection of items, overview, entire set, summary, and conclusions and recommendations. Next. In objectives, the general objectives is select elements of a steam cycle which has a turbine that produces 4,000 kilowatts. In this case, the model is Mitsubishi AT42C. And specific objectives: to analyze the thermodynamically the cycle of a simple steam system, and to select equipment of a steam plant. In the first, I have to start with the Rankine cycle. This is the selection for the analysis thermodynamic. We start with the turbine. This is the Mitsubishi. Later we have a condenser with the analysis thermodynamical. We have the pump, the feed pump, and the boiler.
Now, this is the principal circuit of the steam plant. This is the equipment, the simple equipment, but this plant. In this part is the boiler. The boiler generates, introduce the energy. This energy is inlet heat. this energy generate steam and the turbine and the condenser other energy and pump necessary energy for impulse and liquid in the boiler. Now, this is a thermodynamical analysis. In this graphic presents the cycle of this plant. This graphic is temperature versus entropy. The boiler is part 4:1. In this part is a constant pressure. This is the values. Now, in this part there is a inlet heat. Now, this energy is necessary for calculate the flow on the fuel. Now, next it is the turbine. The turbine is the 2 and 1 and 2 1 to 2. Excuse me. Sorry. And now in this part generate other energy. What is this energy? This energy is the turbine work. This energy is necessary for propulsion of the ship. Now, this part 2 to 3 is the condenser. In this part generate other energy. This energy is out heat. This energy generate because the steam transformate of liquid, yeah, and this part is a constant pressure, and the pump is the part 3 to 4, yeah. Now, for calculate the flow, the vapor and liquid in the cycle, I use this formula. This turbine flow turbine work. This flow turbine work is the power of the turbine. Now, divided by minus variation enthalpy. This enthalpy we calculate for a steam table. Yeah. Now, this is the energy for each equipment. For example, this is the pump work, out heat, inlet heat, and this is the efficient of the cycle. This efficient is net work divided by inlet heat. In this case, we calculate the efficient is equal 30%. That is very satisfactory, because this is a range of the steam on the plant. Now, then they calculate other everything all the energy, and we share and the equipment necessary for satisfy this energy. Now, The equipment we shared for example, in the boiler, when Mitsubishi MB2E. Yeah. The next turbine is Mitsubishi AT42C. The condenser is Thermo-K VH 1218.8. Hand pump is cat pump 6760. This is the principal equipment we shared in the steam plant.
Next. Well, this is the selection of the principal equipment. This is a selection of items and entire overview of all the cycle analysis, the thermodynamical analysis. In resume, this table presents all that we choose with the residue values of the analysis. And resume is the boiler, and these are the requirements that we have in the market, and we choose by the internet data sheet. For the turbine, it's the same. Condenser and feed pump, we took the manuals, and we have to see if that values are made by the analysis that we do. And the summary. Well, we need to select the child components of a steam plant, having a turbine that produces the Mitsubishi 4,000 kilowatts. This 4,000 is entirely for propulsion. After studying the system thermodynamically proceed to find two terms. Here we analyze the real Rankine cycle and determine the basic characteristic of each element of the cycle, for which we use the steam tables and the graph of the temperature versus entropy. Okay. Well, conclusion and recommendation. We detail as possible components of a steam power plant and features a nominal drive about, which produce 40,000 kilowatts the propeller. Each component has been analyzed thermodynamically to find the right characteristics to have.
Okay, thank you. Question, please. How much does it cost?
Well, the cost thus is provided by the plant or the industry, because we took the information in the internet and they only have the data sheet for these elements.
Only technical.
Yes, only technical information, most not values. This is a restricted area for us.
How you evaluate the efficiency of the cycle?
Sorry, can you repeat?
How you evaluate the efficiency of the cycle?
Yes.
With the items. What about?
My partner is answering.
The efficiency of the cycle is 30%. 30%. These values is
many steam plants, many ship building in the beginning they have provided by the propulsion system with the steam plant, but later the costs are very higher, and the engine, diesel engine, two-stroke, replace the turbine system. But some specific ships have steam plants. Only, for example, LNG ships, half of the cargo that this ship have introduced in the boiler for burn and generate energy for introduced to the water part, but transformed to vapor. On other ships, the warships, have nuclear power plants. The cycle is the same. The nuclear plants, it's the boiler for us in the analysis. The reaction in the atoms is the same. The energy introduced to the water, the water transformed to vapor, and the vapor generate the propulsion. It's the same.
Elements, and this is our theme. We're going to analyze the foundations of this vessel. This vessel is the series. The series is a multi-proposal vessel. The dimensions of these ships are 33 meters of length. The breadth it's about 8 meters, and the draft 3.5 meters. Next. Those are our objectives. First, we must say this analysis must stay in the linear system. It's a linear analysis. The units we use in here for the stress are going to be kilograms per square centimeters. For the forces, kilograms, and for the distance, centimeters. First, we are going to model the engine foundations. What does this mean? To model is to see the problem in a simplified way to make the analysis a little bit easier. Then we're going to analyze the stress levels. We must remind that the yield stress of the steel, it's about 2,400 kilograms per square centimeters. So we must stay under these values to have an appropriate design. And at the end, we're going to compare some results because the foundations of the ship, it's about 3 centimeters of thickness, but we are going to give the thickness of 2 centimeters and 1 centimeter. Well, this is the view of the ship. We're going to work in this part. As you can see, we have 2 engines, 2 generators, and we are going to use the symmetry of the ship. So we analyze just one side, because with one side, because the symmetry of the ship is the same values for the other side. Next. Excuse me, could you turn on the light, please? This is a foundation of a machinery room. We want to make this in a program. We're going to use the finite elements using the software SAP 90. So we first start making the base. As you can see in the screen, the length of the base is about 975 centimeters. The spacement between each frame it's about 75 centimeters. We have 4 stiffeners, so we put another ones imaginary to help us in the analysis. So we modeled the base. As you can see, this is the foundation number 1. It's closest to the center line. It will be this one because it's taller, because it's nearest to the center line. Next. and this is the foundation number 2, because it's nearest to the chine. This part is a little bit smaller. So we first generate the base and then a foundation, each one in a separate way, and in the end we join it in the program. We use a text file, so we put it together and they run it on the SAP 90. Then when we have the information, we put it in the SAP 2000, and then we make the analysis.
According to finite elements method, we have to do some restraints to our structure. So we made it in the following way. This could be the center line of the ship. So in this longitudinal, we don't have any rotation on. Sorry, we don't have any rotation in this direction. In this part of the structure, these nodes and the other nodes could be this and this. We consider with the ballhead number 3 and 4. They don't have any rotation on this direction. And the part of the chine that consists with the other part of the hull, they don't have any y-axis displacement or vertical displacement. Please change. Now, referring to loads, we know about reference data, the weight of the motor, the engine, and reductor gear. That will be placed in a kind of structure of like this. So we have to determine how many joints will be placed in. How to know what kind or what part of weight will be placed on each joint? We have to do a relation dividing all the weight of the group of engine and reductor gear by the number of the joints. So if we have around 2.6 tons of the weight of all the group engine and reduction gear, we divide it for 18 joints. We have a value like this: 147.67 kilograms. Now the structural analysis. We can see the gray lines are the original form. Then, if we put here some loops, they will have a new shape. The deforming shapes are represented in the red lines. So, imagine if we put some loops on the top of this, it could be like a structure that try to bend, forming a kind of smiling beam. So that is the same similar behavior. In this case, the loads are here and here, because here we have elements, engine and reduction gear, and here we have the generators. So it will be like a beam, and this will try to bend. Continue, please. Now these are the longitudinal stresses. We can check. Oh, sorry, because these are the section most important, because here are the concentration of higher stresses. We can see it wasn't necessary to use a kind of brackets, because here we have the stresses that have the greatest values, right? Even though the dimension of our foundation are so we are in 3 centimeters of thickness. All these joints have the greater stresses that I said before. That's why here we have more cross section than here. So inertia influence on the stresses. The same cases in here. We have now the transverse sharing stresses. We can check that high concentration of shared stresses are here and here, but here we have the most important. That's why we reinforce this section with the brackets. And these are the transverse stress. We have reflected the highest in this flange of the foundation number 1 and on this part, but we can see these are the more critical. Now we have to do the same pursuit with 2 centimeters of thickness on the in the foundations. We could check that a part of try to bend all the structure, the two foundations try to separate. That other effect. We could see that the concentration of stress compared to the before presentations, we have the same, practically the same. On the same group of joints, we have a high concentration of stress, but they are higher than before because we have here less thickness. But we can see later in advantages analysis that these stresses are not too high, so this structure does work very good. Now here we have the shear stresses. We'll be concentrating here and here, but most important is in here. And these are the transverse stresses. They have the same behavior that before.
Now continue with the procedure. We are going to analyze the same structure with the engine foundation thickness of 1 centimeter. Now for us, this is the worst condition, that is 1 centimeter, 0.8 centimeter in the bottom plate. Now we can see the gray lines are the uniform shape, but the red lines are the deformed shape. Now in 1 centimeter is the greatest value, I approximate in 0.5 centimeters, at least 5 millimeters. Next. Now the stresses. We have here the longitudinal stresses. Now the highest value is 257, located 257 kilograms per square centimeter, located in the joint here, in the highest joint of the bracket number 2, the engine foundation 2. Now we have the shear stress, and the highest value is located in the flange of engine foundation that is a built-in. Now this is the stress in transverse direction, and the highest value is 185 kilograms per centimeter per square centimeter, and it's located in the flange of the engine foundation 2. Finally, to compare, to get the latest objective, we must to compare all the stresses and displacements with the reactions, with the thickness of 3, 2, or 1 centimeter. Now we can see that the worst condition is with 1 centimeter. Now the highest value here is 0.5 centimeters. Now the highest value in stress is 244 kilograms per square centimeter. Now we must to see that is so much lower than the yield stress of 2400 kilograms per square centimeter. Now the conclusions. For the conclusions, we must to see all the objects to model the engine foundation with fan and see all the thickness. First, the modeling get a lot of time because we needed 313 joints and 452 elements. Now that is more time and much expensive. Now the conclusions. The other objective we can see to analyze the structure. In the worst condition of docking, there is a space of 975 centimeters. Still the the shear stress is lowest than the yield stress, but the displacements are so much higher. And finally, we can conclude that in the worst condition, that is the docking plan and 1 centimeter, that is can hold, but that is not recommendable. Thanks. Any questions?
Question, please.
Sorry, ¿qué va a pasar esto?
No questions.
Yes.
So you use or compare recommendation from a ship constructor from a manual calculator for this calculation?
No, we will use a rules or society to know of the engine foundation thickness. Only we must to compare all the variation of thickness since from 1 centimeter to 3 centimeters, no more. Any other question?
Just for some doubts, we were on the docking plan, and we put the blocks in this way. That's why it's the analysis. We put a block right in here and the other here, so it behaves like a beam, and the spacement is really big. So it's the worst condition we can analyze the structure. Not in water, just in duct. So it can fail the structure in that case.
Thank you.